In problem 10.22, we have a hollow spherical shell, and it's rolling without slipping down a slope. So we got a slope like this, maybe. Nope, not like that. But we got a slope like this. And it is rolling down. And it's a spherical, hollow spherical slope, so I had to look up what its moment of inertia is, 2/3 mr squared. This is 38 degrees. And some of the things that they want you to find are the acceleration, they want you to find the frictional force, and they want you to find the coefficient of friction. So that's how we're going to start. So we're going to start by finding the acceleration. First we're going to make a force diagram for this thing. Okay, so for the ball itself, or sorry, for the sphere. Okay, and it's pretty much like you'd expect. We have gravity downward. We're going to have a normal force upward. And we're going to have frictional force this way. Sorry. But again, this is rotating. So since it's rotating, which I'll indicate here again, okay. Not very well though. Oh, okay. Okay. Since it's rotating, let's take a look at where the forces are applied, because that lets us know if there is going to be a torque from any of those forces. Well, gravity is going to be applied from the center. So as gravity is applied from the center, its radius is going to be 0. That means that the torque applied will also be 0. The next force we're going to look at is the normal force. It will be applied from the surface like this. Okay, so that's normal force. Okay. But if you look, it's going to be applied along the radius. So in this case, the force is going to be parallel to the radius. And that's going to make the torque equal to 0. But the frictional force is going to be applied like that. Okay? And the frictional force is going to be the only one that's going to be applied perpendicular to the radius and with a radius that's non-zero, this length along here. So in this one, the torque is not going to be 0. So when we make our Newton's second law for rotation equation, we're actually going to be able to use that force only. It's going to be the only one that we're allowed to use when we make it. So when we look at the force equations, and again, I'm going to tilt my head for this so that I'm going to be breaking the gravitational force into components. So for the x prime component, for just the sum of the forces, if I look at that, it's going to be mg sine of theta minus the frictional force equals ma. We know it can't be all equal because it's rolling down the hill. Okay, and if I add up the y forces, the y prime, remember, because we're talking about down the hill, it's going to be f of n minus mg cosine theta, and that's going to be 0 because it doesn't break that plane. It's going to stay in the plane of the ramp. Okay. And in Newton's second law for rotation, the sum of the torques, well, I'm only going to have one of those. I'm going to have friction, and it's going to be times the radius. So much I can F, I'll do what I can here, equals I alpha. And we know the I is going to be the 2/3 mr squared that we had over here. Now we need to get to work actually determining the acceleration of it. So I'm going to go back to those equations again. I'm going to use the x equation, the mg sine of theta minus f of f equals ma. It's terrible, a. So erase a little bit of that. Okay. And the r, maybe, r times the force of friction equals I alpha. I need to put those together. The main trick is that I'm going to try to turn my my torque equation so that it has acceleration in it and pop it into the other. So I'm going to do that by first sticking in the and substituting frictional force. So first I'm going to get the frictional force equals I alpha over R, and I'm going to make that a capital R, and then I'm going to replace it with a 2/3 mR squared alpha, again all over R. I get 2/3 maybe mR alpha, and alpha R is a special thing. Remember, that's just the acceleration, so it's 2/3 ma. Well, that's helpful to us. We can put that in and replace frictional force with it. Now we don't have anything but m's and a's and theta, or m, a, and theta. We know the mass and we know the angle, so this is all pretty easy now. So mg sine theta minus 2/3 ma equals ma. I'm going to go ahead and kill all these masses and bring this over. So I've got g sine of theta equals a plus 2/3 a. So I've got 5/3 a equals g sine of theta. And that means that a is going to equal 3/5 g sine of, I haven't mentioned the angle yet, they tell us it's 38 degrees. And if I solve that, I get 3.62 meters per second squared. That's the acceleration. That helps too. Okay. I can get the frictional force next too, and that's actually not hard. All I have to do is put it into this equation over here, the 2/3 ma equation, okay, which I'm going to do next. Okay, so frictional force is going to be 2/3. The mass is 2 kilograms, and then I'm going to take times 3.62 meters per second squared. I end up with 4.85 newtons when I put it in my calculator. The last part of part A is they ask you to find the minimum coefficient of friction that you need to do to keep it rolling without slipping. Well, we know that force friction equals mu times the normal force. And since it's on a tilted ramp, we know the normal force is going to be mg cosine of theta. If you convince yourself, go back and take a look at the free body diagram and the Newton's second law equation we made in the y prime direction. So what that means is that mu is going to be the frictional force over mg cosine of theta. In our case, it's going to be 4.85 newtons divided by 2 kilograms, 9.8 meters per second squared, and the cosine of 38 degrees. All that together should give me 0.314. That's what I had. Notice that our units are newtons divided by kilograms meters per second squared. Okay, a newton is a kilogram meter per second squared, so we end up with no unit, exactly what we want for coefficient of friction. Okay. Part D, or part B, sorry, asks how would your answers to part A change if the mass were doubled to 4 kilograms? Well, we saw that our acceleration, we divided the mass out, so that didn't make any difference. So for A, A, no change. B, well, it would certainly change our frictional force. I mean, that would be, sorry about that. Frictional force, well, that would certainly be twice as much. I mean, I had twice as much stuff, right? So we're going to twice as much frictional force, okay? And the coefficient of friction, if you look, this would be twice as much, but this would be twice as much too. So really, that's going to be no change either.